Hi, welcome to my first video on theory of differential equation, and in this video I'll talk on eigenvalue problems. Yeah, eigenvalue problem. Okay, so this video is for students who take subject MTH 4102, MTH 5102. Okay, so for the eigenvalue problem, so what is so in this notes I will talk on what is the eigenvalue problem, how to find the eigenvalue, and eigenfunction. Right, so first we consider the operator Ly, which is given as P naught x y double prime plus P1 x y prime plus P2 x y. Okay, where Px or P naught x is different than 0 and P1 is continuous in interval AB, and the boundary condition is given as B1 y A11 ya plus A12 y prime a plus B11 yb plus B12 y prime b. Okay, and the second boundary condition B2y is given as A21 ya plus A22 y prime a plus B21 yb plus B22 y prime b. Yeah, that's the boundary condition. And B1 B2 are independent, and the rank, yeah, B1 B2 are independent, B1 and B2y are independent, and the rank of those coefficient A11, A12, B11, B12, A21, A22, B21, B22 is equal to 2. Yeah, so what is rank? I think you can refer to your notes in the linear algebra, right? Rank for a matrix. Okay, so the eigenvalue problem. Boundary value problem is given by so we have Ly equal to lambda y, B1 y is 0, B2y is 0. So in this case, lambda we call it as a eigenvalue. Yeah, lambda as a eigenvalue. So the purpose now is to find what lambda is. So that's how we're going to find the eigenvalue, and we plug into the solution, into the general solution of that equation. Then that will give you the eigenfunction. Okay, now if you let phi 1 and phi 2 x lambda be fundamental set, be the fundamental set of Ly equal to lambda y, then the general solution is given by y x lambda is equal to c1 phi 1 x lambda plus c2 phi 2 of x lambda. Okay, and also the boundary condition, yeah, also we have the boundary condition b1y. If you substitute this y into that by, so what we have b1 c1 phi 1 plus c2 phi 2, right? So I can write this as c1 b1 phi 1 plus c2 b1 phi 2, and this is equal to 0. That equal to 0. And for the second boundary condition, we have b2y. So we're going to have c1 b2 phi 1 plus c2 b2 phi 2, that equal to 0. So if you look at these two equations, yeah, so I can write this as a b1 phi 1 b1 phi 2 and b2 phi 1 b2 phi 2 c1 c2, that equal to 0 0. Now this system will have a non-trivial solution. Yeah, that system we have non-trivial solution, which means c1 and c2 you got different than 0. You will have c1 c2 different than 0 if the determinant of that matrix, let's call that matrix A. If the matrix A, the determinant of matrix A is 0. So that's you can see those things easily. So the root of that equation, yeah, the root of that equation will give you the eigenvalue, and clearly the solution y equal to 0. Yeah, the solution y equal to 0 will give the solution of that system. Let's call that system. Let's call that system star. Yeah. So for trivial solution y equal to 0, this gives you a trivial solution for star. Yeah. Trivial solution for equation system star. Okay, now let me give you the formal definition of eigenvalue and eigenfunction. What is eigenvalue and eigenfunction? Yeah. So the lambda, the definition, yeah, lambda, the value of lambda that gives the non-trivial solution, give non-trivial solution to the star. Yeah, we call it as a is called eigenvalues, and the non-trivial solution generated by that eigenvalue, we call it as a eigenfunction. Okay, so the non-trivial solution generated by lambda, and that's eigenvalue, is called the eigenfunction. Eigenfunction, also known as a characteristic function. Okay, if the boundary condition B1, B2, if a B1 and B2 involve only point A and B, then the boundary condition, just we have Ly equal to lambda y, and alpha ya plus beta y prime b that equal to 0, and gamma ya plus delta y prime b that equal to 0, where we need this condition alpha squared plus beta squared, this is different than 0, then gamma squared plus delta squared that different than 0. Okay, so before I go to the example of how to find the eigenvalue and eigenfunction, so let me give you the definition of the self-adjoint eigenvalue. The definition. Now, if we consider a set, DL such that all y which is continuous up to second derivative AB, and with the boundary condition B1 is 0 and B2 is 0, and that's the set of D, then the eigenvalue problem, Ly equal to lambda y for y in that set DL is said to be self-adjoint if we have this condition: integrate AB V Lu minus U Lv that equal to 0 for U V in DL. Okay, so what is DL? DL is a set of y which satisfies that condition, and satisfy also the boundary condition. So the eigenvalue problem Ly, where y satisfies that condition. So in other words, y is the solution of that. Oh, this should be y. So y is the solution to that equation. Then we say this eigenvalue problem with that boundary condition is self-adjoint if it satisfies that equation dx. Okay, now I think in the first part with Dr. Haliza, she has explained to you that the second order differential equation can be made self-adjoint. So I don't want to repeat all those things again. So in this part, I mean the second part, I will focus on the problem of the eigenvalue problem, right? Ly, which is ddx p y prime plus qxy that equal to lambda y with the boundary condition b1 y equal to 0, b2 y equal to 0. Okay, so we are going to find what lambda that satisfy those equations that that give the non-trivial solution to the our what we call that eigenvalue problem, right? And as well as we're going to find what the eigenfunction is. Now let's see some of the example. Let's see example. I have a couple of examples here to discuss. So we find the eigenvalue and eigenfunction of the problem that y double prime plus lambda y that equal to 0 with the boundary condition y0 equal to 0 and y pi that equal to 0. First thing is that we need to find the general solution of that. So what is the particular set of solution of that equation? I think you should know how to find those things. Solution. You just set up the what we call characteristic equation. Yeah. So we have m squared plus lambda is equal to 0. That gives you the root of the equation is m plus minus I sub lambda, correct? No, because you have m squared is minus lambda, so you should get those things. Now for the general solution, we have the complex system here, complex. So the general solution of that equation, so we have y is equal to c1. For that complex, we have cos lambda x plus c2 sine lambda x. Now we apply the boundary condition. We have this boundary condition, so we y equal to 0. So when x is 0, apply the boundary condition. Apply the boundary condition. We have y 0. That give you that one is 0. This is 1. So we have c1. Basically, that gives you 0. Okay. And the second boundary condition, y pi, that give you c1 is 0, that one is 0. So now what we have is c2 sine lambda x is pi, that gives you 0. Yeah, 0 is from the boundary condition. Now if c2 is 0, if c2 equal to 0, then that gives a trivial solution. Okay, what is trivial solution? Trivial solution is y equal to 0. So you can see here, since c is already 0, then if we choose c2 is also 0, you plug in the general solution, you got z0, you got z0, so y is equal to 0. So this is what we call the trivial solution. So therefore c2 cannot be 0. Yeah. So therefore c2 cannot be 0. So what we have, if c2 is not 0, then the other part is 0. So we have sine cert lambda x pi, that one is 0. Yeah. So that you can find what lambda pi, this is n pi, that gives you lambda equal to n squared. Yeah, for n equal to 0, 1, 2, and so on. Okay, so if n equal to 0, if lambda equal to 0, yeah, n equal to 0, so you got lambda equal to 0. So if lambda equal to n squared, which is 0, so what we have, our solution becomes, where's our solution? You can here, we have so we have y just equal to c2 sine, you got that one, lambda is 0, you got 0 times x, that give you 0. So you have a trivial solution. So we have trivial solution. So therefore n cannot be 0. So therefore n cannot be 0. So then the non-trivial solution, if we have n different than 0, so which means n begin from 1, 2, 3, and so on and so forth. Okay, so therefore we can find eigenvalue that we give you the non-trivial solution to our system, which is lambda n is equal to n squared, and therefore our eigenfunction is, you can write that as yn is equal to cn sine square root lambda, which is n, so we have n and x, for n equal to 1, 2, and so on. So this is the eigenvalue and eigenfunction of the eigenvalue problem. Okay, so I think with that one example, I have to stop here. For the next example, I give in the next video. Okay, thank you.